Let's find the maximum deflection and rotation for this beam. Well, if we choose our coordinate x going to the right, and this point is A, and we have point B at the support, then the rotation at B relative to A is equal to the area under the curvature diagram. So the integral of the curvature with respect to x from x equals 0 to L in this case. So if we draw the bending moment diagram, it'll be parabolic and look something like this. And we know that by cutting the beam, you get an equation for the bending moment as minus wx squared on 2. And dividing this by EI gives the curvature. So therefore we're integrating minus wx squared on 2EI over x from x equals 0 to x equals L. And taking the constants outside the integral, so minus w on 2EI, and integrating x squared, we get x cubed on 3, evaluated from x equals 0 to L, so that gives minus wx cubed on 6EI. And you can visualize theta b relative to A as the integral over theta, evaluated from theta A to theta b. So that'll give theta b minus theta A. And we know the rotation at B is 0 for a cantilever. So what you get is minus theta A on the left hand side. And the negatives cancel to give you a positive rotation, which is anti-clockwise at the tip of the cantilever. And that's the maximum rotation. Now to obtain the maximum deflection, we want the distance between the tangent at A and the tangent at B. So we're looking for the tangent at A relative to B, which is this distance over here, is equal to the integral of x by m on EI, which is the curvature. So that was minus wx squared on 2EI, and we integrate over x from x equals 0 to x equals L. So taking the constants outside the integral, we have minus w on 2EI, and then we're left with x cubed, which evaluates the x to the 4 on 4, evaluated from x equals 0 to L. And therefore we get minus wl to the 4 on 8EI. And this here is the maximum deflection for the cantilever. Alternatively, you can use the centroid definition to find the distance between the tangents, which is x bar by the integral of the curvature over x from x equals 0 to L. And we know that the centroid of the curvature diagram is at 3/4 of the length of the beam. So therefore we have 3/4 L, and that's multiplied by this integral, which we already evaluated, which was theta b relative to A of minus wl cubed on 6EI. So doing the algebra will give you the same result. Please subscribe, like and comment to help me reach more students.